Hi everyone, I'm Will. Welcome to this first Hangout in a series of Hangouts related to miniKanren, which is a embedded relational programming language that I've been working on for about 10 years with a number of other researchers and programmers. And this is sort of our first real Hangout in this series, so part of this is going to be meta, trying to figure out exactly what we want to do, talking about sort of the motivation and thoughts I have for how to structure things, and part of it will be technical, and then as we go forward, we'll be spending essentially all of our time on technical things. But I just want, first of all, to welcome people, either who are watching at home after the fact, or who are watching on stream right now, or who are in the chat. We have a group chat bar, which isn't recorded, by the way. So anyone who wants to say anything, go ahead and you can always type in the chat. I'll also be watching Twitter, and probably in the future we can do something like IRC chat and things like that. So anyway, yeah. So feel free, or if you have a question, feel free to just ask it. Just remember to unmute. Okay. So what is this all about? Well, I'm assuming if you're watching this that you've heard of miniKanren or relational programming or logic programming and so forth. We'll get into in a minute what exactly that means. I wanted to talk for a couple of minutes about why I want to do this series of Hangouts and what's interesting about it to me and how I'm hoping it'll be structured. And so I've got some notes on that. So first of all, I think I call this a miniKanren course or something like that on Twitter. That's probably not the best way to describe it, because I would actually like it to be sort of an uncourse. So not a traditional course, and not even a traditional online course. I'd like it to work a little differently. Partly as an experiment to see what you can do with the latest online tools and collaboration, and partly just because format-wise and in terms of learning objectives and all that, I think I would like to do something different from a traditional classroom. So that means we'll be learning about miniKanren and relational programming and logic programming and all that, and programming languages, but there's not going to be homework, there's not going to be deadlines, and I want this to be as collaborative and as interactive as possible. So to me, it's more of sort of mentorship, apprenticeship model that will turn into collaboration, tool development, and research, and things like that. So that's the real goal, and that's what I'm trying to optimize this for. So to give a little bit of background, I've tried. Well, actually, I had a series of miniKanren Hangouts many months ago, and originally my idea with those Hangouts was to try to make the Hangouts accessible to people who didn't know miniKanren. What ended up happening was those Hangouts turned into more of problem solving in miniKanren, and that was good, but I think that it maybe left behind some of the people who didn't have that much experience. So I definitely want to keep the problem-solving aspect and the collaborative aspect, and bring guests on to talk about different aspects of logic programming, relational programming. But I also want to make sure that we are able to bring in as many people as possible and let people learn about logic programming to the extent they can. So I'm going to make a couple of assumptions about the audience, what the audience knows. That's the other thing I've run into with trying to teach miniKanren, is that if you try and teach something like an interpreter for the scheme programming language written in miniKanren that runs forward and backwards and all that, then the person probably has to know scheme. They probably have to know something about interpreters and programming languages, theory, and stuff like that. So what I want to do is sort of minimize the requirements, but I will assume that people have some experience with functional programming, that they have some some knowledge of scheme, and whenever I'm showing something that's a little unusual, tricky, I'll talk about that. But just in order to do anything, I think I'm going to have to assume that people know something about scheme, functional programming. And I'm working on some resources with some other folks to try to give more of that background. But right now, there already are lots of good places where you can get information about scheme and functional programming. So I feel like I really should be concentrating more on the logic programming or relational programming, miniKanren end of things. So that's an assumption I made. Another thing that I've been thinking about is, I really like interaction. So I've tried making some solo videos talking about miniKanren relational programming, and I always found that tricky, both because I'm missing the interaction and also because I'm not sure what's difficult for people. So by making this more interactive, it's a trade-off. I'm not compressing in time as much the information, but I also get better feedback. And so one possibility to try to strike a balance would be to try to edit these videos a little shorter, or at least provide links to different parts of the Hangouts so people can jump forward to what they're interested in. All right. Another motivation for trying this series of Hangouts is that I have a large collection now of very interesting miniKanren problems that I think aren't that difficult to understand what the problems are. You don't have to know that much about logic programming or programming language theory in order to understand why this is tricky, why particular problems are tricky. And solving the problems often involve creativity and engineering and programming skills more than really deep knowledge of theoretical computer science. Maybe they'll benefit from deep knowledge of computer science and programming languages, but sometimes you can make a lot of progress just from being creative or coming at the problem from a new perspective. So I'd like to share some of those problems, or all of the problems, and give people a chance to take a crack at those and to collaborate with people on that, because I think that's really cool. And also, I'm just very interested in trying to figure out to what extent can we do a collaborative, distributed approach to programming and tool development and research. So I'm fascinated by all those things. And part of this also is inspired by some of the communities I think are doing really interesting, innovative things with online learning. One area, or one community I think is doing really interesting work is in the StarCraft community, which is a real-time strategy game. I like watching StarCraft players, and I like watching some of the people who are trying to teach this game, because the game is actually extremely hard. So how do you teach people how to play this game that's notoriously difficult? Turns out that a number of the people involved in that scene have actually figured out how to use the internet and web and online resources really well to teach people. So there's one person in particular, his name's Day9, Sean Plott, and he has a daily series of videos. He's changed it a little bit recently, but he had Fun Day Mondays and Newbie Tuesdays and Friend Day Wednesdays. So, Fun Day Mondays were sort of introductory videos for people who just wanted to learn the basics of StarCraft, and then that was Newbie Tuesdays. It was for newbies. Fun Day Monday is for exploring interesting approaches to playing the game or interesting strategies, sort of experimental. And Friend Day Wednesday, he would bring people on who were friends or people he knew from the scene, and they would talk about StarCraft, and he would learn what they knew. And then on Thursdays, he would review a pro game. And so I think there's actually a lot to be learned from this sort of approach. And for example, instead of reviewing a StarCraft game on Thursday, you could also imagine reviewing, looking very closely at a program, a miniKanren program or a scheme program or something like that, and trying to really understand why the program is written in this style and what trade-offs were made and so forth, right? So that's something I've been thinking about for a long time. Like, how could we kind of draw inspiration from these sorts of approaches? And so anyway, that's another inspiration for me. And so to me, what a successful series of Hangouts would look like is something that's very collaborative, something that was long running, So that's once again sort of an uncourse idea. I'm not thinking of, okay, we'll do 10 of these and then we'll be done or something like that. What I'd like to do is just keep doing these until we run out of steam or problems or something like that, which to me is unlikely. So if there's one other person who's interested, I'll keep doing them. And the other aspect of it that would be really interesting to me is, what sort of problems can we tackle? What complexity of problems can we tackle? Can we work up to real research problems and work up to real tool development that's collaborative? Maybe not all in the context of this weekly hangout, but maybe spawning off some other hangouts where people want to hack on specific problems or problems that are of interest to them. So I would like to try experimenting with sort of pair programming or multiple people programming, working together and working on problems that are of interest to you, all those sorts of things. And also exploring different areas of computer science and programming languages that miniKanren touches upon. So as far as the structure goes, and I certainly haven't figured all this out, but and I'm sure this will change too, but one of the things I was thinking about is, first of all, probably during the first few Hangouts, at least in the beginning of the Hangout, I'll probably be talking the most, just to try to get everyone up to speed with some of the technical background and make sure people are comfortable with the fundamentals of miniKanren programming. But then what I would like to do is, over time, make it more interactive. And even today, I would like to make sort of the second half of this much more interactive and open to discussion and open to some programming and things like that. So that's really important to me, is to make it, even from the very beginning, as interactive as possible. So that's one difference I see between this and, say, a traditional MOOC or online course or just regular course. Especially since many people who are watching this are very experienced programmers, and they may or may not know all the theoretical computer science, they may or may not be experts in logic programming, they may or may not know that much about programming language theory, but there's all sorts of problems that they could definitely tackle. So it's not I want to try to tap into those resources and let people play around with things that they find interesting, and to get feedback from myself and other people on if they write a miniKanren program, okay, what's good about it? What are the trade-offs being made? And also, I'd like to share the code I wrote, right, and see what people's perspectives are on that. So another thing about the structure of this is, just like when I'm teaching a regular class, I would like to have some Hangouts that are sort of special topics Hangouts, or that are longer Hangouts for tackling specific problems. So maybe there are some problems we talk about during these Hangouts, and people are interested in tackling one of those, and we'll actually have another Hangout at non-standard time where we just allocate like 3 or 4 hours and try to solve it, something like that. So I think that's really interesting, because I think that would give a real sense of what it's like to do research in computer science and programming languages. And also, it's just fun. It's interesting to collaborate. And because of the latest tools we have, it's actually sometimes easier to collaborate online than in person. So I think that's really neat, and I'd like to keep pushing that. Another type of special Hangout would be for things that are somewhat ancillary to miniKanren and relational programming, but are still of interest to people watching. So, for example, maybe there are people who want to know about grad school or getting a PhD or what that's about, or they would like to learn more about lambda calculus or combinatorial logic or whatever. Some of those things we could touch on, but some of those things, if we really want to dive into depth, we probably should take that to a different Hangout. But those would be really fun to have, and so that'd be really neat. So having ongoing or fairly regular Hangouts to explore some of those topics, I think, would be really interesting. Also, I would like to have guests. I'd like to have other people who are working on miniKanren come on and share their experiences and expertise, and share what their perspectives are. And I think it's also very interesting to hear from programming language designers about why they design certain features the way they did. And I can give you my perspective on the design of miniKanren, but I'm not the only person who's been involved in the design, and we haven't always agreed amongst ourselves on what's the best way to do things. So that would be really interesting. Okay, so anyway, the moral of the story is I want to keep this fairly informal and as collaborative as possible, and over time make that more and more collaborative once we're all up to speed. And that starts today. So what I'm thinking about doing today is give an introduction to miniKanren and relational programming. Let's briefly talk about that. Talk about sort of the core operators in language, show a couple programs, talk in some detail about sort of what the operators mean. Okay, maybe get a little philosophy about that. And then afterwards, I would like to open it up. And I know there's some people watching who actually have significant miniKanren programming experience or programming experience in core logic or CKanren or some other version of miniKanren, or who've implemented a miniKanren or microKanren. And I'd be curious to see what questions folks have and talk about whatever. And I'd also like to show maybe an open problem that I'm currently working on, a problem that I actually would like to work on tonight if I get time. Show you actually what sort of the cutting edge problems are, or things I don't know how to do. Another important aspect of this is I want to be as open and forthright and intellectually honest as I can possibly be about what I know about miniKanren, what I don't know about relational programming, what things we're bad at, what things miniKanren's not good at. miniKanren is far from a perfect language and has all sorts of problems that I'm aware of every day, every time I try to use it. So I want to talk about all those things as well. Okay, so that's the basic idea. All right, yeah, okay. 100 episodes, that's right. Easy. 100 episodes, easy. Yes, learning is never done. I agree with that too. So, I've been doing research on miniKanren for 10 years, so I hope to be doing it for at least another 10 years as well. And also, when I say miniKanren, okay, here's another thing as far as what topics we want to talk about. And I imagine future episodes, once we've gotten past sort of the basics of miniKanren relational programming, I think future episodes are probably going to have specific themes or specific problems or specific techniques we want to talk about. I'm very interested in the theme of relational programming, viewing programs as relations instead of functions, and that's a little different from Prolog-style traditional logic programming. But miniKanren isn't the only approach to writing relational programs, and I would also like to explore and talk about other models. So there are things like data log or answer set programming, which have a different take. There's also another very interesting language called Gödel that's really about Turing-complete relational programming. So I'd like to investigate some of the models and also just look at Prolog and sort of traditional logic programming and its uses in artificial intelligence and those sorts of things, right? And how you can use miniKanren. What are the trade-offs that are made in Prolog, what are trade-offs made in miniKanren, and we can talk about sort of the language design issues, the implementation issues, and what's miniKanren missing, what's miniKanren just bad at and never going to be good at, and what would be the successor to something like miniKanren. Having learned lessons of miniKanren, maybe it's time for miniKanren to go away and have some other language, that makes different design decisions, play around with that. So anyway, I'm interested in all those topics. All right, so let me check my Twitter real quick. Okay, cool. All right, I think people have found the link now. So we got full house, I think. All right, good. All right. So I guess my first question is, how does that sound to people?
Great to me. Sounds great.
Okay. All right. So some positive feedback. I will say up front that I know that this style of learning is not going to serve everyone's interests or needs. There's some people who they may have a project deadline, and for some reason they have to use logic programming, or they want to use logic programming, and they just want to get up to speed real quick and learn a technique. This may or may not be the optimal solution for those needs. But in terms of longer-term collaboration and trying to make miniKanren and relational programming accessible to a larger group of people who can work on problems, and I think just in terms of optimizing the amount of fun and interesting things we can do, I think this is an interesting approach. And I also, just from a purely educational standpoint, I'm curious to see how far we can push this. I would like to see more of these sorts of collaborative attempts tried. And one reason I'm interested in this is that when I got my PhD at Indiana, I basically did an apprenticeship under Dan Friedman. We would sit together and pair program for, sometimes like 10 or 12 hours a day, hacking on Scheme, hacking on miniKanren, things like that. And I learned a tremendous amount from that experience. So that's sort of collaborative programming, sort of pair programming, but you can even do it in larger groups, I've found out from first-hand experience. I think that's really fascinating, and it's a great way to learn. So I want to keep pushing that aspect of it. Okay? All right. So with that background finished, so I would ask people who are watching this or in chat now to think about how could we improve this as we go forward? What resources could we use? If we want to have a mailing list, that's probably a useful thing to have. Do we want to have a GitHub repo? Do we want to have a wiki? Those sorts of things. How do we want to collaborate? And I'm sure that's thing we'll figure out over time, but we can start thinking about now. IRC, okay, IRC sounds like a great resource. That'd be a great way to have a chat and preserve it. Yeah, so I think I'm happy to set these things up. I'm also happy to let other people set it up. So one of the other goals I have is that if we can actually get a group of people who are interested in these topics, who are working over a long period of time, that it should become self-sustaining. Right? Whenever I try to set something up, be it like a games night or something like that, or whatever it is, I always want to have it be self-sustaining to the point where if I'm traveling or something like that, people would still want to get together and work. I think that's sort of the ultimate goal. And they would have the skills and abilities and everything else. So I want people to feel as much ownership as they can. So I'm happy to set things up. I'm also perfectly happy for other people to set things up. All right, that's all the meta stuff I have. So let's talk about what miniKanren is, and some of this I think people will have seen before if they've watched any of the videos. But I'm going to try to give a little more depth. I'm going to try to go slowly and just give more depth and talk about things. Okay, so for example, equal, the equal operator, which we'll see in a minute, which is one of the 3 core operators in miniKanren, and sort of the heart of traditional logic programming. There's a lot to be said about that operator, and usually we just kind of blow by it really quickly and say a few words about it. But there are at least 1,000 papers written on that operator, probably a lot more than that. So it looks like this kind of little trivial thing, but actually it's not trivial at all. It's extremely deep, and I could talk about that all day. And maybe we should probably have a show one time, or hangout, or whatever we want to call it, just on talking about equal and unification and all the things involved in that. Okay, so I'd rather cover less material and go in more depth, and make sure people feel really comfortable, and because of the way of breaking up the show into here's some stuff I'm going to talk about, and then here's maybe an open problem that I don't know how to solve, and then kind of opening it up to discussion and collaboration. Hopefully we can have a good mix of sort of introductory material and material that's going to be of interest even to people who are advanced logic programmers. And also I hope I can give some interesting perspective on things like equal that maybe people haven't thought about. Because I've thought about the equal operator an awful lot, and so even if you've seen a bunch of miniKanren presentations or done miniKanren programming or Prolog programming, there might be some aspects of it that you haven't thought about. Okay. All right, yeah, so depth is better than breadth. I think that's right. I want to go deep. Okay. It turns out that the core miniKanren language only has 3 logical operators in it, and those operators are very, very powerful. All right, so let's go ahead and start doing some miniKanren. I'm going to try turning on screen sharing. Hopefully this won't crash. If it crashes, I'll just rejoin, okay? Screen sharing is usually when I quit screen sharing, I have problems. But let's see if this works. All right. I'll make it a little bigger. How about that? Can everyone see that all right? Yep. Okay, good. All right. Another thing, and I might have to tweak this on my computer, is that sometimes Google Hangouts will suppress sound while typing. So if that happens, I'll just have to be careful with it, okay?
Will, can you read the chat with your screen share on?
Yeah, so I can read it. Yes, I can still read the chat.
Okay.
Okay, I'll keep that up in the corner. All right. So I'm not going to talk right this second about how to set up miniKanren or what version of Scheme you might want to use, or using Racket or whatever. And certainly we can do a hangout on that or talk about that. But right now, I just want to do a quick introduction to the language. Okay, and if people have questions about that, during the open time in a bit, I'm also happy to give you pointers to that. But this was something we could set up for the website. Right now, I'm just going to assume that you can run miniKanren or CoreLogic or cKanren or any of the other versions of miniKanren out there. And I'm just going to show you the 3 basic operators, the 3 fundamental operators in miniKanren. miniKanren supports other operators and other constraints. I'm not really going to talk about those too much right now. Okay, just let's look at the basics. Okay, so I loaded my miniKanren file and Scheme. I'm going to assume have at least a reading knowledge of Scheme, but if there's something tricky I use, I'll try to explain it. Now that I've loaded Scheme, I've got 3 operators that are defined for me. Okay, and then an interface operator, which we'll talk about in a minute. So, whoops. Okay. Uh-oh. Okay. Make sure this. All right, well, I guess the screen is big now. All right. The first of the 3 operators we're going to talk about is this equal character. And if you type equal and hit return, you'll see that it returns a Scheme procedure. In Scheme, a procedure is like a function. Okay, so it's going to take potentially some inputs and return input. The reason it's a procedure and how it works internally, we'll save for another time. I do definitely want to talk about the internals of miniKanren, how you implement miniKanren, how unification is defined. We're going to talk about all those sorts of things. Right now, we're just going to keep it high level. When you use equal, you give it 2 arguments. It looks like a procedure call in Scheme. In fact, it is a procedure, so this is just a procedure call. And what's going to happen is you call equal with 2 different arguments, like 5 and 5. And what equal represents metaphorically is equality. Okay, in Scheme, we have a notion of equality. We have many notions of equality, actually. And so one notion of equality is Scheme's equal, EQUAL question mark. In Scheme, there are there are two Boolean constants, hash t for true and hash f for false. And we can see that if we ask if 5 and 5 are equal, we get back true. And obviously, if we ask 5 and 6 are equal, we get back false. Okay, so that notion of equality on just numbers matches our intuition. We can also have structured data, not just sort of atomic data. We can have structured data like lists that might contain values. And in this case, equal is going to look at the elements of the lists and compare them. And of course, our lists can be nested in scheme, which really represent trees. You can use equal on trees just as well. So equal can work on numbers, it can work on lists, it can work on nested lists, trees, so forth. And it's going to compare the structure of the lists or the trees and see if everything matches up. Okay, so that's equal. Scheme also has other notions of equality. EQB, question mark, EQ, question mark. There's numeric equality using the equal sign, single equal sign, and a bunch of other notions of equality. And it turns out that in programming and computer science, the notion of equality is actually extremely subtle, extremely tricky. And by choosing the notion or changing the notion of equality, you can get all sorts of interesting behavior as a programmer. And I'll show you one of those examples in a minute. But what I want to show you is the main idea here is that the equal operator on miniKanren is really equivalent to this notion of equality, like notion of schemes equal. Okay, it's really the same thing. If we replace the equal question mark, if we replace equal question mark with equal, then we're expressing some notion of equality. We're basically doing an equality test. Okay, we're trying to see if these two lists, let's say, or nested lists, are the same. And the same according to the notion of schemes equal question mark. Now, in order to actually find out if they're equal, we could just try hitting return. Well, that's not going to give us an answer that we want. It's not going to give us hash t or hash f or something like that. It's just going to give us back a procedure. Okay, so equal, we can already tell, is a procedure that when called with two arguments gives us back another procedure. And we'll figure out why that is in a bit. Not today, probably. But that has to do with the plumbing of miniKanren. In order to actually get an answer out, we need to have an interface between the scheme programming language and miniKanren. miniKanren's generally an embedded language. Okay? You could imagine a standalone miniKanren. miniKanren is usually viewed as an embedded logic programming or embedded relational programming language. And in order for miniKanren to communicate with the language it's embedded in, we need to have some interface operator that will let the host language and miniKanren communicate. And that operator, that piece of syntax in miniKanren is called run. So run is the interface between the host language and miniKanren. So let's try doing run and wrapping the run around this call to equal, and then we can actually see if these two lists we're comparing actually are equal. Syntactically, run takes an argument, which usually is a number, like 1, that tells you how many answers you want to get back. And that's important because miniKanren can return more than one answer. And in fact, for some programs, miniKanren could potentially return an unbounded or infinite number of answers. That's the one there saying we want one answer, if it exists. The Q in the list is what we call a query variable. In this case, we're not really doing anything with the query variable. Basically, query variable is a variable that if we use the variable in the body of the run, we're going to see what the value of Q is at the end of the computation. So we're not using Q here at all. So we're not really going to see anything interesting. We'll use Q in a minute. But the main point is we want to see if this call to equal is going to succeed or not, whether or not these two terms are the same. And when I get back is the empty list. And the empty list is miniKanren's way of representing that there are no solutions. And there are no values of Q for which it's true that the list on the left in the equal is the same as the list on the right. This is the same as saying that these two lists are not the same. They're not equal. So now, of course, I can make two lists that are equal. In this case, instead of getting back the empty list saying there are no solutions, I get back a list of length 1. And it has this weird looking _.0 value. What that _.0 value is actually a representation of our query variable, Q, saying that, yes, our computation succeeded. This holds. These two lists are equal when Q is anything. The _.0 means Q could have any value at all, and those two lists that we're comparing would be equal. Okay? So it's sort of telling you that Q doesn't matter. Q is really not involved in this computation. We can try other sorts of values to compare. So we can check to see if 5 and 6 are the same, and they are not. However, 5 and 5 are the same. And so we can compare all sorts of scheme values this way. If that were the end of the story with equal, it wouldn't be particularly interesting because we could just use schemes equal ? But because we have these very interesting variables in miniKanren that work differently from schemes variables, we can play some more interesting games. So this Q thing, that query variable, it turns out that we can use that inside of a call to equal. So I can write a program like this. Now what I'm asking, I'm really asking a question. That's why we call a Q a query variable. I have a query or a question. I'm asking, is there any value of Q for which Q and 5 would be the same? They would be equal, EQUAL. And the answer, of course, is that yes, there is a value of Q that would make those 5 and Q equal. In particular, Q has to be 5. And I can see that in the answer is return. So I get a list containing one value back, and that value, 5, is the value of Q, which would make the left and right hand side of the call to equal the same. Okay. So in this case, I get exactly what I expect back. If I really wanted to, I could say something even that had a wider use of variables. And this is something you definitely can't write with equal ? In the same way. I could say, is there some value of Q for which Q is equal to Q? And the answer is yes, for any value of Q that's true. And once again, we get the list with the _.0 back, which means Q could be any value. And this would be true. This would hold true. So the way to think about it the way I think about it, there are actually many ways to think about this, but one way to think about it is that equal question mark is a predicate in Scheme. So that's a function that's going to return true or false. And it's going to tell you whether those two terms are the same, according to some notion of what it means to be the same. Equal equal, as opposed to how equal works, equal equal is asserting. It's actually adding a constraint saying that the left and right hand sides have to be the same. Okay? And if that constraint can be satisfied, if there are values for all the variables involved on the left and right hand side that would make those terms the same, as in equal question mark the same, then the program is going to succeed. The computation will succeed. If there is no such value of variables that would make the left and right hand side equal, then the computation is going to fail. So let's revisit the list examples again. And now, instead of having just a quote in front of the list, I'm building up using the list operator in Scheme, which just builds a list. So I'm asking, you could either say I'm asking if list 3.4 is equal to list 3.4, or you could also look at it as I am asserting that list 3.4 has to be the same as list 3.4. Or another way to look at this is to ask, is there any value of our query variable q for which the list 3.4 is equal to list 3.4? Okay, so those are three different ways of looking at this. Okay, so, and it turns out that, first of all, the computation succeeded. We got an answer back. Okay, so that if you're looking at it from the standpoint of, is list 3.4 the same as list 3.4? The answer is yes. Or can it be made the same? The answer is yes. The query aspect of looking at things, is there, what is a value of q for which these two lists are equal? Well, we can see that from the answer _.0, which means any value of q will make those left and right hand sides equal, or will allow them to be made equal. And also we can look at from the assertion standpoint, right? We've asserted that the left and right hand sides, list 3.4 and list 3.4, are indeed equal, and sure enough, the assertion succeeded. Of course, it gets more interesting when we put q inside of one of the lists, because we can put q wherever we want, actually. So now we can look at this miniKanren program in a couple different ways. One way we can ask, well, is there a value of q, or query variable, that would make list q4 and list 3.4 the same, would make them equal? And of course there is. That's when q is 3. So if we run the query, we'll see this. Other ways of looking at this are to ask, or the assertion model, we're asserting list q4 is the same as list 3.4. And that assertion can only be satisfied if q is 3. So there are different ways you might want to look at this program, and different things that it might mean, sort of metaphorically or philosophically, depending on how you want to look at the program. And sometimes I'll look at the same program in different ways depending on how I want to view it. Okay, so there are different ways of looking at this in terms of your own kind of mental model of the world. Okay. Another interesting thing we can do is have more than one occurrence of q in these lists. So we could put a q on both sides of the equal. So now we're asking, is there a value of q that would make these two lists the same? And of course, there is. In fact, there are infinitely many values of q that would make those two lists the same. And that's reflected by the _0 answer. We can ask a somewhat different question. Okay, so now I've swapped the Q and the 4 in the second list, and to make that a little easier to read, let me go ahead and line those up. So now we're saying, or now we're asking, or we're asserting, we can look at the assertion viewpoint, we're asserting that the list Q4 is the same as the list for Q. Okay, so that's an assertion, and miniKanren's job is to figure out, is there a value of Q that would make that assertion true, would satisfy that constraint? And the answer is yes. If Q is 4, then we'll have the list 4, 4 in both cases. Now we can try to make it a little harder for miniKanren. We can try giving miniKanren some lists that can't be satisfied, or some equalities that can't be satisfied. Okay, so going back to our original notion of originally we had list 3, 4 and list 3, 4. We might ask, okay, is there a value of Q that will make these two lists the same? The problem is that in order for those lists to be the same, they're only going to be the same if both lists have a 3 in the first position and if both lists have a 4 in the second position. That's the only way they'd be equal. Because we know the first element has to be 3 because it's the bottom list, and we know the last element in the list has to be 4 from the top list. Unfortunately, we only have one logic variable, or one variable. So they're called logic variables or unification variables. We only have one variable Q here, and that Q would have to simultaneously have the value of 3 and have the value of 4. And there's no way for that to happen. Q can't be 3 and 4 at the same time. It can be one of those, but not both. So that means that there is no solution. There's no assignment we can give to Q, no value we can give to Q that would make those two lists the same. So in this case, there is no answer. And miniKanren can prove there is no answer and returns the empty list saying, hey, there are no solutions to this query, or there's no way to satisfy this assertion, or however you want to look at it. Okay? There's another very interesting way in which miniKanren can fail to come up with a solution through a call to equal. And I'll go ahead and show it to you now because it comes up sometimes. It's very important. So we can go back to this simpler example. We want to know if Q and the list 3 can ever be made equal. And of course they can if Q happens to be the list 3. We can see with our answers that we have a list of answers, and the one answer in that list happens to be the list 3. Okay. Now we might want to change list 3 to actually contain another variable. So instead of 3 in the list, we could actually try putting Q in the list. All right, so now we're asserting that Q and the list containing Q have to be the same value. They have to be the same. Okay, so we're trying to find a value of Q that would make Q and the list containing Q the same. And here miniKanren says that there is no solution. The reason miniKanren says there's no solution is that for Q and the list containing Q to be the same, you would need to have Q be an infinitely nested list. It'd have to be infinitely deep. And miniKanren doesn't allow that. miniKanren could allow that, actually. There are classes of infinite lists that miniKanren could say, okay, that's fine. Q is just an infinite list with a particular structure. But we've decided that we're not going to allow that. And so our notion of equality that we have in miniKanren is over finite scheme terms, or finite scheme lists and pairs and numbers and things like that. Everything in miniKanren all of the individual values that we deal with have to have a finite representation. And not just a finite representation. Metaphorically, you have to imagine that you get instantiated finitely. Make sure that even when there are no variables in that value, it still have a finite representation. So that's an example of something called the occur check that comes up in logic programming, and we can talk about that more later. But that's a very important example of something that will cause miniKanren to fail. To cause equal to fail. If you have a variable and then you have a list or pair that contains that variable, then equal will fail because there's no finite representation of it. Okay. If we go back to this example of the two lists that we're trying to make the same, or unify, is the technical term, we know that this can't succeed because Q would have to simultaneously be 3 and 4, and that can't happen. However, we can make sure that there's an answer as long as we have more than one variable. So let's see if this version of miniKanren that I'm using actually supports multiple variables. All the versions support multiple variables, but not every version of miniKanren supports multiple variables in the run expression up top. Let's see if this works. Yep. Happy day. Okay. So now our run expression has two variables that are query variables, x and y. We're trying to figure out what value is associated with x and what value is associated with y. That would make list x4 and list 3y the same. And we actually found an answer. Sure enough, the answer is list 3, 4. It means that x would have the value 3 and y would have the value 4, and that would make those two lists the same, or equal. And that is correct. So as long as we use multiple logic variables, or multiple variables in our query, we can make those two lists the same. If we try to use a single variable, though, that's not going to work.
So if we have multiple query variables, we get back a list of lists of results. Is that right?
That's right. That's right.
Okay.
And okay, so we've already hit a controversial point with miniKanren, and we've had some big fights about this. The original version of miniKanren only allowed you to have one query variable in the run. Like that. And you could introduce other variables using another operator which we haven't seen yet called fresh, but you could only have one query variable. And I'll go ahead and show you what it would look like. Okay, so now we've introduced two new logic variables, x and y. We call them fresh logic variables because they don't have values yet. And now we can express that unification of the list x4 with the list y3. That succeeds. We get back an answer. We're not getting back the empty list. But notice that we haven't associated our query variable q with any value yet. In order to express the query variable q with a value, we actually need to explicitly do another call to equal to give q a value in terms of x and y. So we would write the full program like this. And now we get back list 3, 4, which is what we had before. Okay, so these two run expressions are equivalent, at least in new versions of miniKanren. Core Logic also supports this. cKanren supports this syntax where you have multiple query variables. So it's very convenient, and one reason we use it is whenever we're trying to do interactive programming like this, it makes our programs much shorter. We can write it much more quickly. one question is, how should the answers be displayed? So if you notice, when we have a single query variable, just the Q, we still wrap that Q in a list. In theory, there's no reason to wrap Q in a list. We could just have run one Q without a list. Something like that. And then, theoretically, maybe you don't need in that case, you don't add any extra parens, and if you have Q in a list, then you add a set of parens around the answer. So it has to do with how do you parenthesize the answers, okay? How many parentheses do you have when you have a single query variable, that kind of thing. And also it has to do with like how consistent do you want to be, and what makes the most sense from the user standpoint. And this is a classic example of programming language design, where we have different things different criteria we're trying to satisfy. It's a form of constraint programming. One problem is we wrote a book, and I wrote my dissertation. We've written lots of papers and given lots of talks and things like that, using the syntax where even when you have a single variable, that single variable appears in a list, and so people are used to having a certain behavior for that. So one thing that was important to me was not to break the existing code that exists, the existing queries, by allowing multiple query variables in a list. Then it's backwards compatible because we never told people how that's supposed to behave. But it also can, in some senses, somewhat inconsistent with the behavior of a single Q in a list. It's like, why isn't that answer wrapped in an extra set of parens as well? So there's some tension there between backwards compatibility and what the users of miniKanren so far are used to, that all the documentation and tutorials we have, versus maybe what's the strictly logical, most consistent meaning of wrapping a Q in a list. So yeah, and I don't know that there's a right answer to that. I think it's, my perspective is I want to keep backwards compatibility, but I also want to be able to have multiple query variables. Okay. Yes, I might want to try using paredit. Yes, I need to try using paredit again. I've tried paredit. It didn't work well with my workflow, but yeah, I definitely could use some of the editing chops of that. Okay. Okay. Peter asked about, does Wadler's law apply here? What's Wadler's law? Is this related to the expression problem or something else? In any language design, a total time spent discussing a feature in this list is proportional to 2 raised to the power of its position. We certainly spent a lot of time, talking about this, and you could argue that we're kind of bike shedding, right? I mean, this is something that everyone has an opinion on. You could be programming a miniKanren for 5 minutes and probably have an opinion about how it should work. And that's because run is the interface into the world, so it makes sense that everyone's going to have a strong opinion about this. And it's an easy issue to understand. Okay, and I think it just illustrates sort of the trade-offs that we've made. MicroKanren makes a very different set of trade-offs than miniKanren does, and we'll definitely talk about that in more depth. Okay, so I've already shown you Fresh, which introduces logic variables, new logic variables, and I've also shown you that Fresh allows you to have multiple calls to equal within it, right? So we can sequence things. Run itself has a hidden implicit Fresh in it. That's another design decision, is that run has a Fresh inside of it that you can't really see, and so run allows you also to have multiple calls to equal.
Well, quick question.
Yeah.
So just so I'm clear, you can use run with multiple variables just like Fresh, and you can, like, in a way, eliminate the Fresh and just use run with multiple variables, or you can use Fresh as well. They're the same thing.
They're almost the same thing.
Okay.
That's a good question. So the difference is that the variables that appear in the query position for run, like the XY, any values of, you're going to see the values of those variables at the end of the computation. That's what's going to be displayed. That's what miniKanren is going to return to you. Okay, so if you wanted to have some variable z, if you need some variable z as like a temporary value, but you don't want to see its value displayed, then you'd want to introduce z using fresh instead of putting it in the list of query variables for run. So that's the real difference, is that anything in that list of query variables after run is going to be displayed, and you may not want to see that because your program might be complicated. It might have a bunch of logic variables, most of which sort of you're not interested in the value associated with those. So you use it to decide what you want to see, what values are associated with those variables. So that's the main thing. Okay.
Okay,
good
got
question. That was a good question. Okay, still sounds like cosmetics in terms of the interface. Yeah, I mean, Paul Graham has this theory that engineers get to do these great things where they design bridges. You get to design the Golden Gate Bridge, something that's like majestic and soaring and beautiful, whereas chair designers spend a lot of time thinking about people's butts, right? I mean, this is when you're thinking about someone's butt, what is comfortable or uncomfortable when the person is using the language day in and day out. So it's not just cosmetics. It's like how awkward is it, or how easy is it to write these little programs, or these little queries, because you actually spend a lot of time writing these little queries when you're doing miniKanren stuff. And also, if you're trying to demo it to other people or do live coding, things like that, then you might be able to radically cut down on how much typing you have to do and things like that. So I'd say it's a little more than cosmetics, but it's not like there's a right or wrong answer. I think it's more about trade-offs. Okay, so I'm going to show you one more use of equal, and then actually I think that's enough for today. I'd rather spend time talking to people, and also I promised to show you a research problem I'm stuck on, but I'd rather get into talking to people and maybe answering some questions they have about miniKanren or starting some discussion or whatever. But I want to show you one more thing about equal. And like I said, I could talk about equal all day, but I'm going to show you one more thing that's interesting, and I think will maybe give you some insight into something that I think, an aspect of logic programming or miniKanren programming that has been intimidating to people or people don't know about, and that's what's called nominal logic programming, which has this very intimidating sounding name, but it's actually a very simple concept. So let me show you what that's about in terms of the equal. Okay, so just a quick refresher on Scheme. In Scheme, we can write the identity function, right? The identity procedure. Lambda XX just takes one argument and returns it. Okay, so you apply this function to some argument, and you just get the value of that argument back. Okay, so here we're applying lambda XX, the identity function, to plus 3 4. So 3 plus 4 will evaluate to 7, and 7, you apply the identity function to 7, you should get back 7. Great, no problem. Yeah, this is nominal logic programming that I'm going to show you in a minute. Okay, so that's great. That all works the way we expect in any functional language, or you can do the same in Ruby with blocks and all that stuff, right? So there's nothing special here. But there is something interesting about this program. I picked the name X as the variable name for my lambda, right? So I said lambda XX. I could have easily picked lambda YY. And anyone who's used Scheme knows that those are supposed to mean the same thing. It doesn't matter. I could have picked any name. In fact, I could have even picked lambda if I wanted. That also works the same. Okay, so in Scheme, as long as you're not overriding or shadowing the name of procedures or variables, something like that, you can pick any name you want as this argument to the lambda. Okay, as long as you're careful to consistently rename things and not avoid shadowing, which is a technical term, basically override the name of a variable, that sort of thing. Okay, but the x and y, I could pick either one. I could have called it z. Doesn't matter. All right, so that's if I'm writing a procedure, right? It doesn't change the behavior. I still have the identity function. Now I could, instead of writing a lambda expression that values a procedure in Scheme, instead I could use like a quoted list. Okay, so I'll create a little quoted list. And here I'm just using Scheme's ability to use quotation to turn something that otherwise would be considered code that's going to turn into a procedure into basically a quoted data structure. It's just going to give me back the list itself. Okay, so I get back lambda xx, that's fine. I can also have quote lambda yy. All right, great. Now let's use our friend equal question mark to see if those are the same. They are not. What about lambda xx and lambda xx? Those are the same. Okay, so that's a little unfortunate in some sense. If we want to think about in terms of the behavior of the equivalent procedures, right? So lambda xx and lambda yy, they represent the identity function. But of course, Scheme's equal doesn't know anymore that we want to think of these things in terms of their procedural behavior, right? We're actually just saying syntactically, we have these two different lists, and they have different symbols inside of them, right? So we just have a list whose second element is a list containing the symbol x versus another list whose second element is a list containing the symbol y. And of course, x and y are different symbols, so Scheme says that they are not equal, which makes sense. Okay, so Peter wants to know if that's where De Bruyne indices come in. Yes, that's exactly where they come in. That's an alternate way of representing lambda terms where you don't actually use the symbols or identifiers or explicit names. Instead, you use numbers to represent basically how many lambdas you'd have to jump over to find the right binding. So lambda xx in De Bruyne would be like lambda 1. And if you wanted to have something like if you wanted to represent that lambda term, in De Bruyne indices, it'd be represented like this. So the 2 says you have to jump over, or you have to jump out to the second lambda, enclosing lambda, to find the binding for that variable. So this is an alternate way to represent lambda terms that avoids using variable names at all. And so Peter's question is very good, and in fact, this is related to a problem I'm working on right now in terms of how to represent lambda terms the best way in miniKanren, or not the best way, but what are different ways to represent miniKanren, lambda terms in miniKanren to do different things. So De Bruyne is one way to deal with the problem of the lambda xx and lambda yy not being the same, because if we use the De Bruyne notation, then lambda xx and lambda yy have the same representation. They would both lambda xx and lambda yy would be represented by lambda 1, which would be the identity function. Okay? That's a representation of the identity function. And for mechanical systems and theorem provers and computer programs, writing lambda terms this way have lots of advantages. There are also some disadvantages, but there are lots of advantages. One disadvantage is that humans tend to like to see the other name, especially if you've been used to scheme or closure or ML or whatever. You're used to seeing lambda terms represented in a certain way. So we might want to keep those identifiers around. So there's another way to think about this. And if we think about it in terms of equal, we can look at this also. Oops. Okay, so first of all, we can, instead of using equal question mark, we can write a little miniKanren program that's going to see if these two lists are the same, right? Is there any association or value of Q that would make these two the same? Of course, any value of Q would make them the same. That's why we get the _0. But we could change lambda XX, one of them, to lambda YY. And now we've failed. Okay, now we failed. They're not the same. We might try to get really clever. Okay, there's another approach, unlike De Bruijn, called higher order abstract syntax, and that's a very powerful technique that's also used in functional programming. And we might try to do the logical programming equivalent of that. And I'm not going to go into too much detail about that right now, but what we could do is try to be clever and use this equal in a neat way where instead of having the symbol x and the symbol y, we could actually use the logic variables, miniKanren's x's and y's, to represent terms. So we could do something like this instead. Okay, so that backquote, that backtick notation is miniKanren, or sorry, Scheme's quasi-quote. Okay, so that's saying that we're treating the data that comes after the backquote as almost constant data. So it's going to be the same as a quoted list, except where we have a comma, also known as unquote, before the data. So that comma x, the comma x means we're going to look up x normally. We're going to evaluate that. So it's going to be treated as a variable, not a symbol. So that's going to be a logic variable, the logic variable represented or introduced by the run. So now our run query is different. It's saying, is there a value of x and a value of y that would make those two lists the same? Okay. And I'll show you another way to write this run in case you haven't seen backquote before. By the way, it came back that yes, there is an assignment, or a value of x and y. Oops. Okay, so I'm just showing a different way to represent the same list, that backquoted list. So I list quote lambda, and then list x, and then x. That's the same as that first quoted lambda expression, or sorry, backquoted lambda. And when you see it written out longhand, you can see it doesn't really look like the lambda expression that we want anymore, so that's why we use the backquote and the commas. But it means the same thing. Okay, in both of those cases, we get back x is _0 and y is _0. What that really means is that x and y are the same value. X and y have to be the same value. In fact, I can prove this to you by getting rid of y. Well, actually, I can't really prove that too, can I? They're going to mean somewhat different things. Okay, I could prove it to you a different way. Watch this. All right. In this case, I'm just saying that there's some term T1, and I'm going to say that that T1, I'm going to assert that that T1 is equal to the lambda XX, and that there's some term T2 potentially different, that's lambda YY. Those things are the same. Now, I haven't said that T1 and T2 are the same. Because I said that they could be different, I haven't said that they're the same, we can see that the value of x is _0, the value of y is _1. That represents that we could have two potentially different values for x and y. X and y could be anything. They don't have to be the same. They could be anything. For any values of x and y, those two lists are the same. That's what it's saying. I could also add one more piece of information saying that T1 and T2 have to be the same. Now I see I get _0 and _0 back for x and y. It means that x and y have to be exactly the same. You know, x could be anything, but y has to be whatever x is in this case. Okay? So now in this case, we've had some way to associate these two terms that we claim both, you know, are supposed to represent the identity function. We can unify them using equal, but we have to be very, very careful because we can also prove this. You know, we want to say x and we want to say the identity function is equal to the identity function. But now I can change the second term. Lambda x y is not the identity function. Okay, so the y that occurs in the body of the right-hand lambda term, that's not bound by that lambda. It's a free variable. Those terms are not the same. But if I try running this, I get back the same answer. It's back that, yes, those terms can be made the same, those lists can be made the same, and x and y both have the same value, _0. So what it's doing is it's trying to force them to be the same. It's by forcing them both to be the identity function. And so saying, okay, well, if they both really are the identity function, they both really are equivalent to lambda XX, then they are the same. But that's not really what I want. I really want more control over the program than that. So there's an approach, or an area of logic or logic programming called nominal logic programming, that basically lets you reason about lambda terms and binding in a nicer way, where you can still use equal, but use a special version of equal that knows about binding. It knows about the scope of variables. It knows that lambda XX and lambda YY really mean the same thing. And that you can pick and choose, you know, the variables as long as you do so very carefully and consistently, and it knows all about that. Okay, so that's really what nominal logic programming is about, and that's very handy when writing interpreters, compilers, type inferencers, and that sort of thing. Okay, so that's what nominal logic is about, and we'll definitely talk about that at some point. And this is also all related, especially the deploying stuff is related to, so my recent attempts to generate combinators like the Y combinator, which you may have heard of, in logic programming, and I think I'll go into detail of that another time, just in the interest of time. But so that's an introduction to the very basics of miniKanren. This equal or unification operator turns out to be at the very heart of logic programming, be it in Prolog, be it in miniKanren, whatever. Okay, and it's really about equality, and you can change the notion of equality. Like Scheme has many different notions of equality. In logic programming, you might want to have many different notions of equality also, like the example of having lambda XX and lambda YY being treated as equal. That's a different notion of equality. So whenever you want to think about changing that different notion of equality, what you probably want to do is change the meaning of equal or have some other meaning of it. And that turns out to be very, very rich, very, very powerful to change the meaning of equality that's used by the equal operator. So in the nominal logic programming is one example of that. Okay. So I think that's it. Let's open up to questions. So one question I see from Adrian is Adrian's trying to do this in core logic, and is doing something very similar to what I just wrote with this query in core logic. Ah, okay. So it turns out if you're writing this in core logic syntax is a little different. The closure syntax is different for the unquote, the comma. In core logic and closure, you would have to write tilde x instead of comma x to do the unquoting. So that's a good point. All right, thanks, Adrian. So let's see if I can copy that code real quick. So in core logic, if you're following along in closure, if you type this in core logic, you'll find that you get back the empty list saying there is no answer. But if you change the x, these x's to tildes, y's, anything with a comma in front of it should have a tilde in front of it. Then that should work in core logic grammar. Okay, good question. Okay, so let me try turning off the screen sharing. Yay, it didn't break. All right, so that's the sort of intro section today, and there's lot more things I could talk about with equal, but that's sort of the quick overview of how it works, and in more depth than we usually get into when we do a presentation on miniKanren. There's a lot to be said about equal and notions of equality, and there's a whole branch of computer science, homotopy type theory, that my understanding is largely concerned with what it means, what equality means. I mean, actually, the notion of equality comes up all throughout mathematics and computer science. It's a very, if you think equality is like an easy notion, you don't understand equality very well. I mean, it's a very, very deep idea, and of course, even the ancient philosophers had all sorts of conundrums related to what it means for two things to be equal. Right? So the more you think about it, the kind of the richer you realize the notion of equality is. So anyway, equal is basically the heart of miniKanren and the heart of traditional logic programming like you see in Prolog. All right, so I guess we're about an hour and a half in. One thing I'm not sure of is how long we should go. And do we want to open up the floor? Do we want to take a break? Do we want to, call it a day? Do we want to?
I've got some questions.
Yeah. Okay. So I'm happy to hang out. For quite a bit longer. And if people want to talk and ask questions, that's cool. If they've got to leave or whatever, that's understandable. And if people have open problems that they're trying to solve in miniKanren, we want to talk about those or do a little hacking, whatever. Okay, so Ambrose has got a question. Richards, you've got a question. What scheme do you recommend for miniKanren as a pretty universal? I use Vicari scheme, which is a free, it's actually a GPL 3 version of scheme. It was started as Icarus scheme at Indiana. My friend Aziz created it. Now it's been forked. It's called Vicari scheme, Vicare. And Vicari scheme, I think it installs easily under Linux. It installs under OS X using Homebrew. There's a Homebrew spell and the Homebrew cask or something that Michael Valentine has created to install it under OS 10 with OS X without too much difficulty. I've never tried installing it under Windows. I don't know how easy that is, but that's the scheme I use. You can also use Racket. One way to run in Racket is if you could take a scheme version of miniKanren and run it under the R6 language mode. That's one way to do it. And another way is to use cKanren, which is a Racket-specific implementation of miniKanren at this point. You could also run, of course, core logic and closure. There's also one more scheme thing I should mention. There's a bKanren implementation or BigLoo, which is a version of Scheme. That seems like that's quite complete, so you might want to check out BigLoo Scheme also if you're a BigLoo user. I think BigLoo is a little different from the other schemes I've used, so I haven't used that one directly. But in theory, any R5 or R6 RS compatible scheme should run at least the basic miniKanrens with little or no changing. And if anyone wants to port miniKanren to other schemes, I'm happy to help them. All right, good question. Ambrose, did you had a question?
Okay, so I'm going to put a form into the chat that we used before. This list y3 equals list 4y. So why can't we just say that y equals 3 and 4?
Like it has a set of values or something like that? Or
I don't know, like unification is a pretty subtle thing, and it seems like maybe there's a subtle answer to that. I don't know.
Okay. All right, so let's see if I can, for folks at home, let me try starting up screen sharing again. Okay, so Ambrose has this interesting question, which I like. The question is going back to this run1 q, or run1 y, let's say, of equal list y3 and equal list 4y. And if we line them up, we see that y would have to be 4 and y would have to be 3 at the same time, right? Whoops, run. Okay, and Ambrose wants to know why can't y be 3 and 4 simultaneously? That's an interesting question. Well, probably it can be 3 and 4 simultaneously, right? I mean, basically what I'm trying to demonstrate with the nominal logic programming is that there are many different notions of equality, right? And in fact, if you look at different logics, if you want to implement those as the basis, if you want to implement a logic programming language based on some specific logic, often that involves changing what equality means, or that might be part of what you do, is change the notion of equality. So, you could totally come up with a notion of equality where y is 3 and 4 at the same time. Maybe you have some sort of set of possible values y can have, right? And you want to maybe reduce that set or grow that set over time. That would be one way of looking at it. I'm sure there are lots of other ways. Peter suggests maybe in a temporal logic. I'm not sure. But that's a very good question. I mean, that's exactly the sort of question that I think is really good when someone who I think that's really good to ask these sorts of questions, right? Because at some point in time, I just kind of internalized that, yeah, y can't be two things at once, but there's no reason it can't be. You'd have to figure out what that means, and what other rules kind of go along with that. So that's a very interesting challenge. Try to come up with a logic programming system or a version of miniKanren or some other system where y could be 3 and 4 at the same time. What would that mean, and what would that let you do that you can't normally do? Do you have any specific ideas for that, Ambrose?
See, I'm in a similar boat to you. I know that it's absurd, but then I watched you program it, and my immediate response was, well, you could kind of imagine a crazy world where they're simultaneously 3 and 4. That's about as far as I got.
Yeah, I mean, I don't think that's absurd at all. So for example, we don't allow in miniKanren the list containing Q to unify with Q itself, okay? Because we say that violates the occur check, and we say that this fails. But there are notions of unification used in logic programming where you do allow that. Now, standard Prolog allows that just because they don't want to do the expense of checking that a variable occurs inside some other term or list. Okay, so but they don't really want you to do that. That's not considered correct. You're supposed to avoid it, but they don't want to do the check. But there are also other versions of Prolog like Prolog 2, I think, has this, that allows you to do unification over what are called rational terms, and that includes infinite terms that can be expressed finitely, where you have sort of this sort of infinite recursion or infinite depth of the term. That's perfectly allowed in Prolog 2, I think. Certainly in later Prolog 3, Prolog 4, all these constraint logic.
Like that example that you showed, equals equals q list q would be expressible in Prolog 2.
Yeah, and you could, I mean, we have to go out of our way in miniKanren to disallow that. Okay. So what the way we would handle that in miniKanren, or one way we can handle that, is allow that unification to happen. It'll happen by default. The logic variable q will be associated with the list containing q. That part happens fine. We don't have to change anything about miniKanren to make that happen. The tricky part is when you want to print out the answer, because if the answer has q in it, then when you print out the answer, or when I shouldn't say print out, when you return the answer, when miniKanren returns the answer, it's going to try to return the value of q. So, okay, what's the value of q? It's a list containing q. Okay, so it's going to create the parens for the list, and then say, okay, what's the value of q? It's a list that containing q. So you're going to get back this infinite, nested set of lists, and it's never going to stop producing lists. But one way you can do that, and Scheme already lets you create data structures that have circularities in them. And Scheme, for example, and I think Vicari also, they check when displaying a representation of a term with a circular data structure, it will actually create some sort of finite representation of the circular data structure, showing you where the circularities are. So you could do exactly the same thing with miniKanren, right? So that's totally reasonable. Okay, so Dan's saying maybe the variables would have a list of possible values they can take, right? So I guess one question would be, are there times you're not going to succeed? Like, what would it mean to fail? Would you ever fail with this model where a variable can have more than one value, or under which circumstances would you want to fail? If I unify y with anything, does that always succeed? Or are you just building up a set of all possible values y could take on? One area that could be useful in is in things like abstract interpretation used in static analysis, where you want to build up a list of all the possible values, that could be taken on, by some variable or things like that. Usually there you want to collapse values, right? So you might have sort of an abstract notion of a value, and you're collapsing, in some abstract notion of garbage collection, abstract notion of stack locations and things like that, and you might want to collapse those to some extent. But I can imagine, doing something like that. You could have some notion of logic programming where every query succeeds, right? Where you're not failing, you're just building up all the possible values you could encounter, right? So that's an interesting question. I haven't seen a version of logic programming that lets you have y be simultaneously 5 and 6, let's say. There are also set constraints where you're reasoning explicitly about sets, and that you could explicitly add these values to a set, right? So this feels like this is related to the notion of sets to some extent, but in that case you can also fail because you say something's not in the set. So that's interesting. The other way to look at it would be just to look at it from a logic level, right? Like Peter said, maybe in temporal logic, like look at all the logical systems that have been created. Are there logical systems where you can have two values simultaneously? It also comes up in quantum mechanics, by the way, right? Where you can have a superposition of states. And there are many interesting connections or similarities between quantum mechanics and logic programming. Many, many connections, which would probably be worth talking about sometime. So that, maybe you can have y is either 3 or 4. In a sense, y starts out as either 3 or 4 or 5, or it could be one of infinitely many values. But you could also have a notion of, y is either 3 or 4 at this point in time, and when you unify y with 3 and 4, it puts it in some superposition state or something weird like that. The aspect of traditional logic programming that makes this tricky is that in traditional logic programming, once you know something, you're not allowed to ever go back and say you don't know that anymore. So that can be somewhat tricky. If x is 5, everything you do from then on has to be consistent with x being 5, that kind of thing. So some of these schemes, when you're trying to think about what they might mean, they can run into problems where you violate that, or you're going to have to relax that notion. And there are notions of logic programming like defeasible logic, which allows you to have notions of changing your mind or having, you have some default rules that are overridden, right? So maybe in special cases, your normal reasoning doesn't hold anymore. You have special cases that override those rules and so forth. So people have looked at what does it mean to have non-monotonic logics where when you add knowledge, you might contradict things that you thought you knew before, that kind of thing, right? So this might be like a non-monotonic logic. I'm not sure. Let's see. How would having y bind to 2 different values simultaneously be different than splitting y into 2 variables, y1 and y2? Well, I guess it's a sharing type thing. It feels like y has associated with it like a structure of possible values it can contain instead of just having 2 totally independent variables. Can't we wrap a list by a thunk and then have a co-list? Peter asks. So that I think is related to notions of co-induction. Peter, is that right?
Well, can you hear me now?
Yes.
Okay, great. So I was just thinking about that uncourse check that you mentioned, that you can't unify Q and the list of Q. So if you would overload, let's say, a list constructor by a lazy one, the one that you would need to force before you can even know that it's a list, then I guess you could have some kind of a co-inductively defined notion of a queue, which is a list of queues.
Yeah, so that's a very interesting question, and that's something I'd like to explore more. So I think most programmers or computer scientists or mathematicians are used to the notion of induction and inductive proofs and recursion and writing recursive definitions. There's also a notion of co-induction and a notion of co-recursion, where you can reason about infinite objects, like infinite streams of values and things like that. One interesting aspect I know of where co-recursion comes up is related to something called tabling, and definitely I want to talk about that at some point. Tabling is the logic programming equivalent of memoization, the idea of remembering previous values you've generated. So the traditional example is something like the Fibonacci function, which if you write sort of the naive version of Fibonacci, then you redo a lot of the work every time you call Fibonacci. It has to call itself recursively. You end up redoing a huge amount of work, and it makes the running time of the algorithm exponential. Turns out there's a way to make that much faster by saving work that you've previously done and then looking up the values you've computed for a procedure call instead of actually redoing all the work. So that's memoization. And there's a logic programming equivalent. It's trickier in logic programming than it is in functional programming for 2 reasons, at least. One reason is that you have to be able to handle terms or arguments to a procedure call that have logic variables in them where you don't know the value yet. So it's a little trickier to tell when 2 calls are equivalent. The other thing that makes it tricky is that when you call a logic, when you call a function or what we call a relation, logic programming world, you can get back more than one answer, which we haven't looked at yet. But you can get back multiple answers. You can get back a stream of infinitely many answers even. So handling that properly makes implementing tabling is trickier than implementing memoization. But the interesting thing is that once you have implemented memoization, or sorry, tabling, then it's not too hard, apparently, to add some notion of co-inductive logic programming, where you can do logic programming over certain classes of infinite objects very, very nicely. So one class of infinite objects, like we said, is if you do unification or equal without the occur check, you can have certain notions of an infinite object. But this is dealing with infinite streams of answers. And that's there's been a lot of good work on that out of University of Texas, Dallas, UT Dallas. Gopal Gupta's group has done a lot of work on co-inductive logic programming built on top of tabling. And since we have a tabling implementation on miniKanren, that actually would be a really interesting area to explore, would be how hard would it be to add some notion of co-inductive logic programming, how far could we push that, and also, are there other notions of co-inductive logic programming that aren't related to tabling? So Peter's question is good, and I think when we get into some of the implementation of miniKanren and implementation of tabling, I think we'll see some of these ideas come up over and over again. Yes, a link to the Texas research. I can put up a link to, I guess maybe I should create a wiki or something, or we should create a wiki or something for sharing links, or a mailing group or something. So I can definitely send links out to those papers and resources. What are the questions that co-inductive logic programming would allow us to answer? That's a good question. I don't really know. My understanding is that the co-inductive logic programming research that's come out of UT Dallas allows you to program with infinite streams of values that have very specific structure. So it's not like you can just do anything you want. It has to have a specific structure to the stream. Like I don't know if you can do something like generate all the digits of pi using their co-inductive logic programming approach. I don't really understand because I haven't used it. Okay, so maybe you can, but at least the talk I saw on this a couple of years ago led me to think that you couldn't. But I don't know. I mean, I'd have to, we'd have to play around with it. We'd probably want to implement it, and then we'd have a much better understanding of what you can do. The other thing is that even if we implement something that other folks have already played with, miniKanren has its own, its own features that that I don't think any other logic programming or functional or any other programming language has quite that combination of features. So even if we implement something that another group has done and don't change anything, just try to get that part working, sometimes we would do very interesting things in miniKanren that maybe other people haven't thought about or couldn't express very easily because our language has different design decisions and features. So it'd be very cool to implement tabling and see where we could push that. Yeah, so that would be really, so that's exactly the sort of thing I'd like to do, right? Is that explore some of these issues and implementations and start playing around with this. And like tabling in miniKanren something, or sorry, tabling in miniKanren something I'm investigating again right now because I want to. There are a couple things about tabling in miniKanren that don't work well. One is that we don't handle all the constraints in miniKanren. Another problem is that our tabling implementation isn't very efficient. There are lots of ways to improve the efficiency that are pretty obvious, but we just haven't put in the engineering effort. And another is that there's some restrictions. You have to be very, very careful when you use miniKanren's tabling system right now, or you'll get incorrect results. And without an error message or anything like that, it will make it look like it proved something that it didn't. And that always bothers me. I always want miniKanren to not let me look like I'm proving something when I'm not. So improving miniKanren to be able to handle constraints, to run faster, and to error out or be able to handle more gracefully some of these other situations where you'd be proving something you're not really proving. It just looks like you're proving it. Those would also be really cool things. Did we say what tabling is? So tabling is the logic programming equivalent of memoization, where you're saving. The reason it's called tabling is that you basically are building up a big table of partial results or final results from calls to miniKanren goals or relations. And so if you're familiar with miniKanren, if you make a call to append or appendo in miniKanren, it's going to return certain answers. Could return many answers or infinite list of answers, right? So the idea is that whenever a call to a miniKanren goal that's tabled returns an answer, miniKanren sticks the answer in in this table, and the next time, or the stream of answers in the table, and the next time miniKanren makes a call to that goal with the same arguments or equivalent arguments, then instead of redoing the whole computation, miniKanren just looks up in the table that stream of answers and then returns that new stream, or that stream of answers, so you don't have to redo the computation. The reason that people care about memoization in functional programming, let's say, or just in imperative programming or whatever, is that it can make your program much more efficient. It can actually change the complexity class, reduce the complexity class of your computation. And that's also true in logic programming, but there's another reason that makes it even more important in logic programming. It can be the difference. Tabling can actually make programs that would otherwise go in an infinite loop in logic programming, make them terminate. So that's a really powerful property. And there's the canonical example of that is trying to find all the paths through a directed graph that has a cycle in it. And we can definitely look at those examples when we talk about tabling. But you can actually have programs that would otherwise go in an infinite loop, and if you table the program, it can come back finitely. In fact, immediately, like almost immediately. So that's very powerful. The trade-off is that not all programs benefit from tabling, and there's a memory cost to tabling. So the worst case is if you never reuse if you never make the same call again, then you're just wasting. You're adding all these entries to a table, hoping to reuse information in the table based on a subsequent call to that goal. And if you never make the call, then you're just wasting all the time of sticking things in tables, checking all the calls, and also you're wasting a huge amount of memory. You'll run out of memory, and it'll make your program slower. So not every program can benefit from tabling, and even understanding which programs can benefit from tabling and how to do the tabling right is a little subtle. But it's a very interesting topic, and it is related to co-induction and dealing with infinite streams of values and things like that. So it's very deep also. Yes, it's the memoization for logic programming, and it's trickier than memoization, but also has some cool things that otherwise you wouldn't get from memoization. Okay, so we're coming up on 2 hours since we started. That's about as long as I was planning this. Oh, the research problem. Yeah. Okay. So one research problem is adding constraints to tabling. Okay. So I'll just since we were talking about tabling, I'll just talk about that one instead. I've got a giant list of research problems. I was going to talk about a different one, but the tabling one's good also. So miniKanren has other constraints besides equal, which is the equality constraint or unification constraint. There's symbolo, which is a constraint saying that the argument to symbolo has to either be a logic variable with no value or it has to be a scheme symbol. There's numbero, which says this argument has to either be a scheme number or a logic variable that if it becomes associated with something in the future has to be a number. There are other constraints that we have. There's finite domain constraints to deal with numbers. There's this absento constraint, disequality constraints. Disequality is the opposite of equal. It's saying that two things have to be different. They can never be the same. So we've got all these constraints, and we want to add more. The problem is our current tabling implementation only works with equal. It doesn't work with any other constraints in our system. So one of the tricks is, like, how do we do that? What's the right way to handle tabling with constraints? And apparently, this is still very much an open problem. Like, there's not a well-known, understood way to do this in general. There's been a lot of research on tabling, but I haven't really found much research on tabling and constraints. So I think, and my understanding also is that there hasn't been much research recently, that people haven't really tackled that problem for a while. But there is an implementation of Prolog called XSB Prolog that's out of Stony Brook, and that has a very sophisticated implementation of tabling. I don't know what sort of constraints they can handle other than unification, but that would be a place to look. Okay, so why is it tricky? Is because of the monotonicity requirements of tabling? It's tricky in a couple ways. One is, and I think this part can be handled probably not without too much difficulty. One problem is, how do you know when two calls are equivalent, right? We have a way to handle that when we just have unification. Like I said, tabling is trickier than memoization because, if one of the arguments is the list containing the logic variable x, and x is not bound, this is a fresh logic variable, right? Then if someone calls, if there's a call to that same relation later that's tabled, and instead of the list containing the fresh variable x is the list containing the fresh variable y, those should be considered the same call. But you could also have constraints on x, saying x is fresh, but it has a symbolic constraint on it, or it has this equality constraint on it, or things like that. So figuring out really what the right thing to do is, and when to consider two calls to a table goal to really be equivalent. First of all, that actually doesn't even have a single answer. There are many ways you can, just like there are different notions of equality, there's different notions of equality when you're looking at arguments to a table goal. So trying to figure out what the best way to look at, or what's a reasonable trade-off in terms of figuring out the equality of the goals is important. You can do these subsumption tests, which are expensive, but allows you to treat a wider range of arguments as equivalent. That has some performance implications, but it allows you potentially to reuse the tabled values more aggressively. And I think when you get into all of the constraints, then it gets even more complicated to try to figure out what's the right way. When do you want to consider these two terms, these two calls to be equivalent? I've had some recent thought about that. I think that's okay to handle. But I think the trickier thing, and it probably has to do with our implementation of tabling more than anything else, more than a fundamental restriction, is how do you reuse the answers? Okay, so if you make a call to a relation that gives you back 50 answers, if those answers are just instantiating logic variables through unification, it's pretty straightforward to figure out how to reuse those answers. Once the goals start, the table goals starts adding constraints to the terms in arbitrary ways, then it gets a little trickier to figure out how are we going to make sure subsequent calls all the arguments of subsequent calls are going to get the right constraints on them. And part of that is related to the fact that we don't have a great architecture right now for adding constraints or imposing constraints. So our constraints right now are very much hard-coded into the system. So it may be that a better constraint architecture would make it much easier to implement tabling with constraints. But I would be happy even to have a hard-coded tabling with constraints system, even if it made it tricky to add new constraints. So those are, I think, the two biggest issues. And I have thoughts on this. I think I'm ready to take a crack at adding constraints to tabling and also speeding it up. Ramana Kumar and I worked on the tabling implementation a number of years ago. Ramana was the person who did most of the implementation effort. So, and maybe he would be willing to ask. But anyway, I can very clearly, I think, explain the tabling problems. By the way, if anyone's interested in learning more about tabling and miniKanren, the implementation of it, and what it's used for, I just last week retypeset my dissertation, or this week, I guess, retypeset my dissertation to make it easier to read. It used to be double-spaced font, so single-spaced. So if you look on miniKanren.org, or if you look on miniKanren.org, you'll find a link to my dissertation retypeset that's easier to read, and also I released the dissertation under Creative Commons license, attribution. Basically, people can use it any way they want. They could even release it commercially without my permission now or whatever. So, if you want to look at my dissertation, there's a chapter on tabling. There are two chapters on tabling that go into quite a bit of detail about how it works. And I just reread that this past week. And also, I'd be happy to go over the code. If anyone wants to do hacking sessions, explore that, I'd be happy to do that also. All right. So, yeah, I guess we're at 2 hours now. I think it's probably good to go ahead and end the Hangout. Let people go. If anyone wants to hang out for a few minutes and just talk about any meta level stuff, like how can make this work better in the future. See you, Austin. Thanks for joining us. I'd be happy to talk about that. Otherwise, take it offline, talk on Twitter or whatever, and email. And be happy to hear what people, any suggestions, topics, talk about, different ways to make things more interactive, whatever. All right. So I hope in the future things will, we'll be able to get to the point where it's not mostly me talking, that it's much more collaborative. It might take a few hangouts to get to that point where everyone's comfortable. But I'd like to start moving towards that as quickly as possible. All right, thanks a lot. I'm going to stop the broadcast, but I'll hang out if people want to talk about it. Bye.